Welcome to this problem walkthrough. In this session, we'll explore problem number 58, titled Length of Last Word. We'll break it down step by step, analyze different approaches, and understand the most efficient way to tackle this challenge. Let's dive in. The problem we're working on is called Length of Last Word. Here's the task. You are given a string, S, which is made up of words and spaces. Your goal is to determine the length of the last word in this string. Now, a word is defined as a maximal substring that only contains non-space characters. This means a word ends when you encounter a space or the end of the string. Let's take a look at the input and output format. The input is a string S, where the length of the string is between 1 and 10,000 characters. The string can contain both uppercase and lowercase English letters, along with spaces. Importantly, the string may have leading spaces, trailing spaces, or even multiple spaces between words. The output is a single integer, which represents the length of the last word in the string. Let's explore the first two examples to understand this better. In example 1, the input string is S equals hello world. The task is to find the last word and determine its length. Here, the last word is world, which consists of 5 characters, so the output is 5. Now, in example 2, the input string is S equals fly me to the moon. Notice that this string has leading and trailing spaces, as well as multiple spaces between the words. After trimming these unnecessary spaces, the string becomes fly me to the moon. The last word here is moon, which has 4 characters. Therefore, the output is 4. Now, let's look at example 3. In this case, the input string is S equals Luffy is still Joyboy. There are no leading or trailing spaces, and the words are separated by single spaces. The last word in this string is Joyboy, which has 6 characters. As a result, the output is 6. Additionally, let's consider the constraints for this problem. The length of S will always fall between 1 and 10,000 characters. The string S will only contain uppercase and lowercase English letters as well as spaces. Importantly, there will always be at least one word in the string, so you don't have to worry about handling completely empty inputs. Finally, the string might include leading or trailing spaces, and there could be multiple spaces between words. Now let's think about some edge cases that might come up. First, consider a string with only one word and no spaces, like S equals word. Here, the single word is also the last word, so the output would simply be the length of that word. Another case is when the string has leading and trailing spaces, such as S equals word. In this scenario, you need to ignore those extra spaces and focus on the word itself. Similarly, strings with multiple spaces between words, like S equals AB, require you to handle those gaps correctly and identify the last word. Finally, think about strings where the only non-space content is a single word, for example, S equals word. These examples highlight the importance of accounting for spaces while reliably extracting the last word and determining its length. To solve problem number 58, the goal is to determine the length of the last word in a given string. A word is defined as the longest sequence of characters without spaces. One straightforward way to tackle this is the brute force approach. Here, we split the string into an array of words using spaces as delimiters. After splitting, we can simply return the length of the last word in the array. This method is intuitive because it leverages built-in string operations to handle edge cases like trailing spaces automatically. For example, if the string ends with spaces, the split function will ignore those and still give us the correct result. The algorithm for this is concise, as it only requires splitting the string and accessing the last element. However, while this approach is easy to implement, it does have some trade-offs, particularly in terms of space usage, which we will explore further. The brute force approach operates with a time complexity of O(n), where n is the length of the string, as the split function needs to iterate through the entire string once. However, its space complexity is O(k), where k is the number of words in the string, because splitting creates a new array to store these words. Although this method is simple, the extra memory usage is a notable drawback, especially for large input strings. To address this, we can use a more optimized approach that avoids creating additional data structures. Instead of splitting the string, we can iterate backward through the string to find and count the characters of the last word directly. This reverse iteration technique minimizes memory usage while still maintaining efficiency. By starting at the end of the string, we can skip trailing spaces and quickly locate the last word, counting its length one character at a time. This eliminates the need for extra storage, making it a more space-efficient solution. The reverse iteration approach is not only memory efficient but also operates with a time complexity of O(n) as it scans the string once from end to start. Its space complexity is O(1) since no additional data structures are created. This makes it a highly efficient solution. However, this approach does come with its own challenges, as it involves manual iteration logic. While this logic avoids unnecessary overhead, it can be prone to implementation errors if not handled carefully. As an alternative, we could use a trimming and string manipulation strategy. In this method, the string is first stripped of trailing spaces using strip, and then the position of the last space is identified using refined. The length of the last word is calculated based on the substring after the last space. This alternative approach is compact and avoids manual iteration, but it requires careful handling of edge cases, such as strings with no spaces or strings that consist of just one word. Both methods are viable, but each has its trade-offs. Among the approaches discussed, we chose the reverse iteration method as the optimal solution. It offers the best balance between time and space efficiency. With a linear runtime and no additional memory usage, it scales well for large input sizes. While the brute force approach is simpler to write, its use of extra space for the array makes it less appealing for scenarios where memory is a concern. On the other hand, the trimming and string manipulation technique is concise but less intuitive, and it introduces potential pitfalls with edge case handling. The reverse iteration approach, however, combines efficiency with straightforward logic, making it a robust and reliable choice for this problem. In this problem, we're tasked with finding the length of the last word in a given string S. The string may have leading, trailing, or multiple spaces between words, and a word is defined as a sequence of non-space characters. To solve this efficiently, we use a reverse traversal method, which allows us to directly focus on the last word, skipping unnecessary computation. The first step in the algorithm is to understand the intuition behind reverse traversal. Since our goal is to determine the length of the last word, it's logical to start from the end of the string. This way, we can skip trailing spaces and immediately count the characters of the last word. Next, we initialize three variables, n, the length of the string, length, which will store the length of the last word and is initially set to 0, and I, the index pointer, which starts at the last character of the string, or n1. The first step of the traversal involves skipping trailing spaces. As long as I is within bounds and the current character s, I, is a space, we decrement I. This ensures that when we start counting, we're positioned directly at the end of the last word or at the beginning of the string if no words exist. Once trailing spaces have been skipped, the next step is to count the length of the last word. Starting from the current position of I, we enter a loop. As long as I is within bounds and s, I, is not a space, we increment the length variable and decrement I. This loop continues until we encounter a space or the start of the string. By the end of this step, the length variable contains the exact length of the last word. Finally, we return the value of length as the result. This algorithm is both space efficient and time efficient. It doesn't use any additional data structures, relying solely on a few variables, which keeps its memory usage minimal. Additionally, by starting at the end and stopping as soon as the last word is processed, we minimize the number of operations, achieving a linear time complexity of O(n), where n is the length of the string. The algorithm also handles edge cases effectively. For instance, if the string is empty or contains only spaces, the result will be 0, as there are no words to count. For strings with a single word, the algorithm correctly returns the length of that word, regardless of whether there are trailing spaces. The algorithm only requires two variables, length, which tracks the length of the last word, and I, which serves as the index pointer for reverse traversal. This simplicity ensures minimal memory usage. To better understand the process, let's walk through an example. Consider the input string s equals hello world. First, we initialize the variables. N is set to 17, the length of the string, length is initialized to 0, and I is initialized to 16, the last index of the string. In the next step, we skip the trailing spaces. At I equals 16, s, 16, equals a space, so we decrement I to 15. We continue this process until I reaches 10, where s, 10, equals the character d. Now, we're positioned at the last character of the last word. The next step is to count the length of the last word. Starting from I equals 10, we increment length to 1, as s, 10, is d. We continue decrementing I and incrementing length for each character of the word, stopping when I reaches 5, where s, 5, equals a space. At this point, length equals 5, representing the length of the last word. The final step is to return the value of length. In this example, the last word is world, and its length is 5. Therefore, the algorithm returns length equals 5. Now, let's discuss the complexity of the algorithm. The time complexity is O, n, as we traverse the string at most once in reverse. This includes skipping trailing spaces and counting the characters of the last word. The space complexity is O, 1, as we only use a few variables and no additional data structures. The algorithm also handles various edge cases effectively. For an empty string, the output is 0, as there are no words to count. For a string containing only spaces, the algorithm skips all spaces and correctly identifies that no words exist, returning 0. If the input string contains a single word without trailing spaces, the algorithm counts the length of that word and returns it accurately. Now, let's consider the case of a single word with trailing spaces. For example, if the input is hello, the algorithm first skips the trailing spaces until it reaches the last character of the word. It then counts the characters of the word hello, resulting in a length of 5, which is returned as the output. To reinforce our understanding, let's review the code implementation. The function length _of_last word first calculates the length of the string and initializes the length variable to 0 and I to the last index. It then enters a loop to skip trailing spaces, decrementing I while the current character is a space. Once the trailing spaces are skipped, the second loop counts the length of the last word by incrementing length and decrementing I until a space is encountered or the string is exhausted. Finally, the function returns the value of length. This concise implementation mirrors the steps of the algorithm and ensures efficiency in both time and space. In conclusion, this algorithm offers a simple yet effective solution to the problem of finding the length of the last word in a string. By directly targeting the last word and skipping unnecessary processing, it achieves optimal performance with an O, n, time complexity and O, 1, space complexity. Its ability to handle edge cases, such as empty strings, strings with only spaces, and strings with a single word, makes it a robust solution. The reverse traversal method ensures that we focus only on the relevant portion of the string, avoiding any wasted computation. This combination of efficiency, simplicity, and reliability makes the algorithm an excellent example of problem-solving in string manipulation tasks. This Python solution efficiently calculates the length of the last word in a given string s by iterating from the end of the string. The function length of last word is implemented within a class solution, as per LeetCode's requirements. First, the code initializes a variable I to the index of the last character in the string, len, s1. This ensures we start processing from the end of the string. A while loop is then used to skip any trailing spaces, decrementing I until a non-space character is encountered. This step handles cases where the input string ends with spaces. Once the trailing spaces are skipped, another while loop begins, which calculates the length of the last word. This loop continues as long as I is non-negative and the current character is not a space. Within this loop, the length variable is increment for each character that belongs to the last word, and I is decrement to move to the previous character in the string. Finally, the function returns the calculated length. This approach ensures that the solution is efficient, as it avoids unnecessary operations and directly targets the last word by processing the string in reverse. The algorithm handles edge cases such as strings with only spaces, strings with a single word, and strings with multiple spaces between words effectively. The time complexity of the solution is O, n, where n is the length of the string s, as the algorithm processes each character at most once. The space complexity is O, 1, since no additional data structures are used. This makes the solution both time and space efficient, suitable for handling large input strings. This is the Java implementation of LeetCode problem number 58, length of last word. The logic mirrors the Python solution, where we iterate from the end of the string to skip trailing spaces and then count the length of the last word. Key differences include explicit type declarations in Java and the use of Java's charAt method to access characters in a string. The code is concise and adheres to Java conventions, ensuring clarity and correctness. To solve the problem of finding the length of the last word, we begin with the example input string hello world. First, we initialize our pointer I to the index of the last character in the string, which is 10. Since there are no trailing spaces in this input, we skip the step of removing spaces at the end. Now, we proceed to count the length of the last word. Starting from the last character, we check if each character is not a space and increment our length counter for each valid character. At index 10, the character is D, so we increment the length to 1 and move backwards. At index 9, the character is L, so the length becomes 2. This process continues as we encounter R, O, and W, incrementing the length each time until we reach index 5, where a space is encountered. At this point, the loop terminates, and the final length of the last word is determined to be 5. We return this value as the output. Now let's analyze another example with the input string fly me to the moon. Here, the string contains leading and trailing spaces, which we need to account for. First, we initialize I to 29, the index of the last character in the string. To skip the trailing spaces, we decrement I repeatedly until we find a non-space character. This brings I to 24, pointing to the character N. Next, we count the length of the last word by iterating backward and checking each character. At index 24, the character N increments the length to 1. Then, at index 23, the character O increases the length to 2. Continuing, we process another O and M, bringing the length to 4. When we encounter a space at index 20, the loop stops. The length of the last word, which is moon, is therefore 4, and we return this as the output. Finally, let's consider the simplest example with the input string A. Here, the string contains only one character without any trailing spaces. We initialize I to 0, the index of the last character. Since there are no spaces to skip, we move directly to counting the length of the last word. At index 0, the character is not a space, so we increment the length to 1. We then decrement I to -1, which ends the loop as we've reached the start of the string. Since the entire string forms the last word, its length is simply 1. This value is returned as the output. To analyze the time complexity of our solution, we start by looking at the initialization of the index variable I. This operation, which calculates the length of the string and subtracts 1, is a simple arithmetic computation and takes constant time, or O, 1. Next, we have the first while loop, which is responsible for trimming trailing spaces from the end of the string. In the worst-case scenario, where the entire string consists of spaces, this loop will iterate through all n characters of the string, resulting in a time complexity of O, n. After this, we encounter the second while loop, which calculates the length of the last word by iterating through its characters until a space or the start of the string is encountered. Again, in the worst case, where there are no spaces in the string, this loop will process all n characters. However, it's important to note that both loops together will never exceed a total of n iterations, as they work sequentially. Thus, the combined time complexity of these two loops is O, n. Following the loops, we reach the return statement, which simply outputs the computed length. Since this operation involves no iteration or complex computation, it executes in constant time, or O, 1. When we combine all the operations, the overall time complexity of the algorithm is dominated by the two while loops, making it O, n, where n is the length of the string. Shifting our focus to space complexity, we observe that the input string s does not contribute additional space, as it is not modified or duplicated. The algorithm uses only a constant number of auxiliary variables, such as I4 traversing the string and length 4 storing the result. Since no additional data structures like arrays or lists are used, the memory usage remains constant. Therefore, the overall space complexity of this solution is 1. This efficiency in space usage is further emphasized when comparing the current approach to a brute force method. A brute force approach might involve splitting the string into words using Python's split method and then finding the length of the last word. For instance, we could implement it as follows. The method splits the string into a list of words and then accesses the last word to compute its length. While this approach has a time complexity of n, due to the split operation, it introduces an additional space complexity of n, because the split method creates a list to store the words. In contrast, our current approach avoids this overhead entirely, achieving the same time complexity of n, while maintaining a more efficient space complexity of 1. By comparing the two approaches, we see that both have an identical time complexity of n. However, the current approach is more space efficient, using only 1 space, whereas the brute force method requires n space to store the list of words. Now, let's break down the best, average, and worst-case scenarios for our solution. In the best case, the string is empty or consists entirely of spaces. Here, the first while loop terminates immediately, and the overall time complexity is n. In the average case, the string contains multiple words separated by spaces. The algorithm skips the trailing spaces and calculates the length of the last word, and the time complexity remains n, as the algorithm processes each character at most once. In the worst-case scenario, the string contains no spaces and consists of a single long word. In this case, both while loops will iterate through the entire string, making the time complexity n. To confirm this, we can use a mathematical proof of big O. Let n represent the length of the string. Each character in the string is processed at most once across the two while loops. This ensures that the total number of operations grows linearly with the size of the input, resulting in an overall time complexity of n. Furthermore, since the algorithm does not use any additional data structures and only relies on a constant number of auxiliary variables, the space complexity remains constant at 1. This balance of efficiency in both time and space makes the solution highly optimized for this problem. When working on this problem, there are several common mistakes to watch out for. First, not handling trailing spaces is a frequent issue. If you assume the last word always ends at the very end of the string, strings like hello world with extra spaces at the end can lead to incorrect results. The fix here is simple. Use the strip function to remove any leading or trailing spaces before processing the string. Another common mistake is misinterpreting empty strings. For example, inputs like an empty string or a string with only spaces, such as, can cause errors during splitting or indexing. To avoid this, explicitly check for empty or whitespace-only strings in your solution. Inefficient string traversals are another pitfall to avoid. Traversing the string multiple times unnecessarily increases time complexity, especially for large inputs. Instead, aim for a single-pass solution or minimize operations. Lastly, using split instead of split is problematic because split doesn't handle consecutive spaces correctly, while split automatically accounts for all types of whitespace. These are some of the most common areas to pay attention to when solving this problem. The issue with using split is that it fails to handle consecutive spaces properly, whereas split, without arguments, automatically handles all whitespace, making it a more robust choice. Overcomplicating the problem is another frequent mistake. Some implementations use custom logic to find the last word, even though Python's built-in methods, like split or a simple reverse traversal strategy, are sufficient. Adding unnecessary complexity increases the likelihood of introducing bugs. From an interview perspective, it's important to remember that string manipulation problems often involve edge cases like empty strings, trailing spaces, or multiple spaces. Always verify these scenarios, as interviewers tend to test for them. Additionally, aim for optimal space usage. For instance, solutions that avoid creating intermediate data structures, like lists, can achieve O(1) space complexity. Clear communication is also key during interviews. When you explicitly explain how you handle edge cases, it demonstrates thoroughness and strong problem-solving skills. Be prepared for variations, such as inputs with punctuation, extremely large strings, or even edge cases involving multilingual or Unicode characters. In some variations of the problem, the input may include multilingual text, which requires proper handling of Unicode characters. This is something to keep in mind for robustness. Now, if you're looking to practice related problems on LeetCode, there are several worth exploring. For instance, Problem 151, Reverse Words in a String, focuses on whitespace handling and word extraction, which is similar to this problem. Problem 186, Reverse Words in a String 2, emphasizes in-place reversal, which requires optimizing for space efficiency. Problem 14, Longest Common Prefix, introduces another string manipulation challenge that involves careful handling of edge cases. And finally, Problem 434, Number of Segments in a String, is directly related, as it focuses on counting words or segments in a string. Exploring these problems can help you further refine your skills in string manipulation. Now let's look at a couple of approaches you can use to solve this problem. One approach is to use Python's built-in split function. By stripping leading and trailing spaces, splitting the string by whitespace, and returning the length of the last segment, you can solve the problem efficiently. This method is simple and easy to implement, but it does use O(n) extra space for the split list. For example, the solution would look like this. First, call strip on the string, then use split to divide it into segments, and simply return the length of the last segment. Alternatively, you can take a reverse traversal approach. This method involves traversing the string from the end, skipping any trailing spaces, and then counting characters until you encounter the next space. This approach is more space efficient, with O(1) space complexity, but it can be slightly more complex to implement. Here's how it works. Initialize a counter for the length and start from the end of the string, decrementing as you skip spaces and count characters. Both methods have their trade-offs, so choose the one that best fits the constraints and requirements of the problem. Great job on making it to the end. To recap, we solved the length of last word problem by applying efficient string manipulation techniques. Keep practicing these types of problems to build confidence for interviews. Remember, consistency is key. Thanks for watching, and I look forward to seeing you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!